Welcome, everyone, to another exciting episode. Today, we're diving into a fascinating area of process systems engineering, inverse mapping. Brian and Amy are here with me. I'm excited to learn all about it from them.
Thanks, Emma. Inverse mapping is essentially about solving what are known as inverse problems. Think of it like this: normally, we understand how a system works, and we can predict the outcome. But what if we know the outcome and want to find out the causes?
Exactly. A simple analogy would be diagnosing a car problem. You observe the symptoms: the car won't start, or it's making a strange noise, and you want to figure out what's causing those symptoms. That's an inverse problem, figuring out the why from the what.
That makes sense. So, what are the typical challenges in solving these inverse problems in process systems engineering?
Traditionally, we've relied on methods like nonlinear programming to solve these problems. But these can be computationally expensive, especially when you're dealing with complex models and high dimensionality. It can take a lot of computing power and time.
Right. And that's where this new approach comes in. It uses something called automatic differentiation, coupled with the implicit function theorem, to tackle these inverse problems more efficiently.
Automatic differentiation and implicit function theorem, those sound a bit intimidating. Can you break them down for us?
Sure. Automatic differentiation is basically a way to compute derivatives of a function automatically and accurately. Think of derivatives as measures of sensitivity. How much does the output of a process change when you tweak the inputs? Automatic differentiation does it for you precisely. It removes a lot of approximation errors that happen when you estimate the derivatives numerically.
And the implicit function theorem helps us relate changes in the inputs of a system to changes in the outputs, especially when the relationship between them is complex and not easily expressed in a simple equation. So, even if you don't have a simple equation, this theorem still helps to relate the derivatives of inputs to the derivatives of the outputs.
Okay, I think I'm starting to get it. So, how does this approach work in practice? Can you give us an example?
The paper discusses a couple of case studies. One is a continuous stirred tank reactor, a CSTR. Imagine you want to design a reactor that produces specific amounts of chemicals. The inverse problem is, what reactor parameters, like its radius and operating temperature, do you need to achieve those desired output concentrations?
Using this new approach, you can map the desired output concentrations back to the required reactor parameters. It figures out the combination of radius and temperature that will give you what you want. It's like reverse engineering the reactor design. You start from the products and then figure out the processing conditions.
That sounds incredibly useful. So, what are the main benefits of this approach compared to the traditional methods?
The biggest advantage is the reduction in computational time. Because automatic differentiation is very efficient at computing derivatives, and because this approach directly tackles the inverse problem rather than using something like iterative optimization, it can find solutions much faster than brute force methods or nonlinear programming.
Also, this method can handle nonlinearities really well. Chemical processes are often highly nonlinear, meaning that small changes in the inputs can lead to disproportionately large changes in the outputs. This approach can capture those complex relationships effectively.
Are there any limitations to this approach? Are there situations where it might not work so well?
Yes, there are a few potential issues. One is model discontinuities. If your model has sudden jumps or breaks, automatic differentiation might run into problems. The software might return a not a number value. In those cases, you need to investigate the output space region, because there might not be a valid solution.
Another challenge is bifurcations. These are points where the solution to the inverse problem becomes non-unique, where you have multiple possible input conditions that lead to the same output. In such cases, you might need to use continuation methods to navigate these bifurcations and find all possible solutions.
So, what's the big picture here? What are the potential future applications of this method in process systems engineering?
This approach really opens up a new way of thinking about design and manufacturing problems. Instead of starting with the inputs and trying to predict the outputs, you can start with the desired outputs and work backward to find the required inputs. It's a more goal-oriented approach.
And because it's computationally efficient, it could be used to solve large-scale problems that were previously intractable. For example, optimizing the design and operation of entire chemical plants to meet specific product demands or environmental targets. The ability to solve the problems effectively means that chemical engineers can be more creative about the solutions.
That's incredibly exciting. So, to summarize, this new approach uses automatic differentiation and the implicit function theorem to solve inverse problems in process systems engineering more efficiently than traditional methods. It can handle nonlinearities well, but it has some limitations related to model discontinuities and bifurcations. Overall, it offers a new and creative way of tackling design and manufacturing problems.
Exactly. It's about flipping the problem on its head and starting with the desired outcome.
I would also say that it's important to remember that this method allows us to deal with complex and nonlinear problems, leading to better and more realistic chemical solutions.
Well, that's all the time we have for today. Brian and Amy, thank you so much for sharing your insights on this fascinating topic.